All right. So just confirm if you can see the slides.
Yes, sir.
Yes,
Okay.
sir.
All right. So today we'll discuss about number systems and how to add numbers, how to build circuits which will add numbers. And why we are starting number system is because numbers are everywhere. Almost everything that we do in a computer or any other digital circuit is a sensor network or something deals with numbers. So it's sort of the earliest things that people did in a digital circuit was to represent numbers and manipulate or do operations on the numbers. We'll start with the simple addition operator and then we'll go to other operators. But before that, let's see how do we represent numbers. One just thing I want to state is that this representation of numbers, of course, the number systems you know very much from your PDS, you know very much. But let me add here the focus in our case, as opposed to the PDS treatment of the number system, is that our goal will be to design circuits, design digital circuits which will work with this number. So our everything will be geared towards that. Okay, so all of you know that the most, the number systems are almost universally, except for some early systems, use a positional system or a radix system. So any integer n, initially let us consider only positive integers n. Any integer n can be expressed in this form. So you have a set of digits which we call am minus 1 up to a0, and then fractional parts a minus 1 up to a minus p, and corresponding to each of these digits, depending on at which position the digits appear, you have a weight. Okay, so the weights are powers of each other. So the 0th position has a weight of G1, a to the b to the power 0, and the other as you go to the left, the most significant bit part, you have b square, and so on, b to the power m, and so on. Okay, and as you go to the right of the decimal place, you have b to the power minus 1, b to the power minus 2, up to b to the power minus p. So b to the power m is the most significant position because it has the highest weight, and b to the power minus p is the least significant position, which is because it has the lowest weight. Note that this is kind of universal in the sense that the decimal number system can be represented this way. Okay, so the binary number system can be represented this way. So this b is called the base of the number. It may be 2, it may be 10, it may be other values. And this m, these are the powers, m minus p, these are the power of the bases, which increases as you go towards more significant bit and decreases as you go towards the least significant bit. And this am, a1 up to a minus p, these are the digits. The requirement is that the value of these digits has to be from 0 to b, 0 to b minus 1. They has to be from 0 to b minus 1. So now let us consider an example. Let us consider b to be the decimal number system. So b is 10. So the value of the digits can be from 0 to 9. And the positional weights are 0, 1, 2 as you go to MSB, and minus 1, minus 2 as you go to the LSB. So this number you can see 1, 2, 3 point, that a decimal point, then 4, 5. Okay. So 1, 2, 3.45 is in this radix system is actually means this. Okay, so this symbol, this string 123.45, if we convert it to a number, would be, sorry, I withdraw. I said n to be an integer, n can be a float number also. The part of the number to the left of the decimal point is the integer part. The significant bit is a weight 10 to the power 0 or 1. The fractional part is to the right of the decimal point. It has a weight so this is the part. This has a weight from b to the power -1 to b to the power -p. So this I think more or less all of you know. Keep in mind the MSB and the LSB part, and by our convention we'll go from left to right. Left is MSB, right is LSB. There is no particular reason, because we write it that way, we are writing it that way. Now the common bases can be decimal. They can be which is 10, binary 2, octal 8, and hexadecimal 16. For example, 1101, then the decimal point 1001 is equivalent to the decimal number. This thing, if we convert it, if we look at the value in the decimal system, it comes out to be 13.25. So naturally, you can see that similarly, suppose I have a number, note that the value of the integers can be from 0 to base -1. So if you have a base 2, it can only be 0 and 1. If it is base 4, it can be from 0 to 3. So 3, 1 decimal, then 1 in base 4 would be 1 into 1 plus 3 into 4. It is 12. 12 and 1 is 13. And 1 to the power 1 into 1 by 4, which is 0.25. So this 31.1 base 4 is also 13.25. Similarly, you can check 15.2. It is 8 plus 5, 13, and 2 into 2 by 8. This is also 13.25. So the same number, I mean, just the digits change as we change the base. Among these, the binary number system is what we will adopt in any digital system, because of the plain reason that since you have only 2 digits, 0 and 1, note that these bases are kind of implicit. So if you want to represent a number, you just need to represent the digits. The bases are implicit in the rule, in the representation rule, which is nothing but this radix system, am into bm, b to the power m plus am minus 1 into b to the power m minus 1. The value is implicit in this rule. That's the advantage of any positional number system. When India produced the first positional number system in the world, this was the advantage. You can represent any number by an implicit rule of digits. So the only thing you need to communicate or convey or store are the digits in sequence from the MSB to LSB. So since in a binary system there are only 2 digits, 0 and 1, there are only 2 things you need to represent. You need to communicate, you need to store, you need to manipulate. There are only 2 digits. As we have discussed in the last class, these 2 digits can be represented by 2 voltage levels representing low and high. And there are the circuits that we dealt with are nice properties. You can easily manipulate them. You can reliably maintain them. There is no ambiguity. I mean, you can distinguish easily between 2 voltage levels, even if the voltages vary a little bit. This would have been really difficult. Suppose you have a system where, let's say, you have to represent 10 different voltage levels. Okay, there would be such a circuit would be much more complicated. Such having building transistors and other things to build such a circuit would be even more complicated. So that just because of the implementation aspect, the decimal system, the binary system becomes more popular. Okay, so I think this is clear, and so far we have represented positive numbers, an integral part and a fraction part. We have not yet represented negative numbers. We will see that you also can have a nice convention for representing negative numbers using the rule of complementation. using the rule of Gauss. I'll come back to that, but let's for the moment deal with only positive numbers. So here are some examples of representing numbers in various bases. So you can have bases like 2, 4, 8, 10. By the way, I talked about two more bases, octal and hexadecimal. So decimal is what human beings understand, binary is what computers understand. But computers, as I told you, because of the device limitations, have problem in understanding decimals, whereas humans, they have some difficulty in understanding binary because the binary strings, the binary digits, even for small numbers, would be pretty long. You have to use a read. You have to read a big string. One in decimal, just 99. In binary, it will be a very long string. Okay. So to avoid, so to kind of hit a middle ground, you have the octal and hexadecimal numbers, which are kind of an intermediate stage where it's easy to see the decimal equivalent. It is also easy to see their binary equivalent. So when human beings read binary codes, they don't read binary codes directly. They convert binary into octal and hexadecimal, which is a more compact representation, and then read the binary, read the octal and the hexadecimal numbers. It is easy to convert octal to decimal. Similarly, it is easy to convert octal to binary also. You can see that 8 is somewhere in between 2 and 10. Okay, so here are some representations. The bases are 4, 8, and 16. You can see 16, which is the hexadecimal, has digits from 0 to 9, and remaining has A, B, C, D, E, F, capital. Similarly, 12 has 0 to 9, then alpha, beta, then 10, 11, 12, 13. 10 has all these things. Okay. Oh no, I think this is not 10, 11, 12. This is just, the representative is only up to alpha, beta. These are 2 digits, not single digits. Similarly, this is plain and simple base 10. You have base 8, you have 1 to 7, and then you have 2 digits. These are, after that, these are 2-digit numbers, and 4 and binary. So I think this is obvious. All right. So naturally, if you are having so many number system, you need to convert between them. You need to convert bases between them. So if you have to convert a number in base B1 to the same number in base B2, let's see what are the rules. Let's take case 1 in which B1 is less than B2. B1 is less than, for example, if B1 is 2 binary and B2 is 10. So you want to convert binary number to a decimal number. So what you simply do is to use the arithmetic of B2. Use the arithmetic of B2. So if you want to convert binary to decimal, use the decimals arithmetic. If you want to convert base 8 to decimal, use the decimal arithmetic. So if you want to, if n is your number in base 1 B1, you simply use this radix expansion. So let's take an example. Suppose I have a base 8 number 432.2 base 8. I want to convert it in decimal. So what I'll do, I will just use the decimal arithmetic. How I'll use the decimal arithmetic? I'll just expand this number. I'll use the radix representation, which is 4 into 8 square plus 3 into 8 to the power 1 plus 2 into 8 to the power 0 plus 2 into 8 to the power minus 1. Okay, so just use decimal arithmetic, and this is the decimal equivalent, 282.25. Similarly, binary to decimal, you just use decimal arithmetic. Use the why I am saying that this is the decimal arithmetic. See, because this powers. Hello. Because the powers are represented as decimals, right? The powers are represented as decimals. So this will be 2 keep. Sorry for the typo. So this is 2 cube plus 1 into 2 square, 0 into 2 to the power 1, 1 into 2 to the power 0 to the power minus 1 into 2 to the power minus 2. So you see these weights, they are now decimal weights. We are treating them as decimal values, and these digits also we are treating as decimal value. So you just do decimal arithmetic. If B1 is less than B2, you just use the arithmetic of B. Let's take the converse case. If B1 is greater than B2, that means, for example, you want to convert decimal to binary. Let's do it in the following way. So B1 is greater than B2. So n, what is nB1? What is the representation number? Let's look at the original representation, because originally the number is in base B1. I want to find out the digits if I convert to base B2. So this is the number in base B1. Let's say it is m into B2 to the power Bm. So this is in base B2. Okay, let's say this is in base B2. So what I do, how do I get nB1? What I do is that I divide it, okay, by B2. That gives me the least significant digit of the number in base B2 is the remainder. Okay, so you can easily see, if you divide it by B2, you get A0 by B2 as the remainder. The rest of the thing is the quotient is divisible by B2. Okay, so this is the remainder. So if you get the remainder, that's give you the least significant bit of the integer part. And this you can, because if you just look at Q0 and again divide by B2, you get A1, similarly A2. So you go on doing this till Q0 becomes 0 terminate. Okay, otherwise you keep on recursively doing it. What you do for the fractional part, you do the reverse. So it is B2 to the power minus 1. So you multiply to A minus 1, you multiply by B2. So this becomes B2 into B2 to the power minus 1 into B2 is 1. So you get minus 1. And you get a remaining part. And you keep recursively doing it till it becomes this part becomes 0. Okay, this part becomes 0. Yes. So you recursively doing it. So you get A minus 1, A minus 1, A minus 2, and so on. I think this you all know. So this is an example. Let's say I want to convert decimal 548 into octal base 8. So what I'll do is that I'll divide 548 by 8. Divide 548 by 8. The quotient is 68. Remainder is 4. And I divide 68 by 8. Quotient is 8. Remainder is 4. I do it. Note one thing, that if you write down the digits, they would be in opposite order, because you see I have been doing it in the opposite order. First you get A0, then you get A1, and so on. So if the remainders are 4, 4, 0, and 1, the corresponding octal representation would be 1044. Okay. Similarly, let's say I want to convert 345 decimal to base 6. I will keep on dividing 345 by 6. I get quotient 57, remainder 3, then 57 again by 6, you get 9, and remainder 3, and so on. And so I get 333. I have to go the opposite order, so I get 1333. Okay. Any doubt regarding this? Any doubt? I think this all you know. These are simple. Maybe even in high school you studied all this. I'm just recapitulating. Okay, so so this is how you do that. The only thing you can probably pay a little bit notice is that these rules probably you know, but these rules simply come from this rule of division. Simply come from this simple rule of division. If you want to convert B1 to base 2, keep on dividing B1 by B2. Keep on dividing B1 by B2 and look at the remainder. Okay, and this would give the least significant, second least significant, and so on, those digits. Do I need to tell I don't think I need to do further examples. I think this is all clear. And this is just a recapitulation. So any question on this? Any chance? Did I miss anything, or did I do some? I hope I'm audible.
Yes, sir, you are audible.
Yeah, good. Thank you. Okay, so this is clear. This is pretty simple. Okay, so this is about the fractional part, what I told. Instead of dividing, you have to now multiply. You have to cancel out. So to get a minus 1, you have to multiply. This coefficient is, its weight is b2 to the power minus 1. So if you multiply by b2, this becomes just a minus 1. So for example, if I convert 0.3125 base 10 to base 8, I would multiply 0.3125 by 8. I'll get 2.500, only the integer part. Similarly, the fractional part, again I multiply by 8, I get 4, I keep the integer part. I go on doing this till the fractional part is 0. So a minus 1 is 2, a minus 2 is. So now I write it in the same order. Because you see now for the fractional part, the most significant bit is first recovered and the second most significant bit. So I write it in the same order. So 0.3125 base 10 is 0.24 base 8. One thing to be noted, I think it is obvious from this procedure, is that the number of digits may vary between bases for the fractional parts. So not only for the fractional parts, for the integer parts also. And one thing that may happen for the fractional parts is that a recurring fraction in one base may become a finite fraction, finite number of digits in another base. Whereas a finite number of digits in a particular base after the decimal may lead in another base representation may lead to an infinitely recurring number of digits. Okay, and the precision, this is one thing to be noted. Other thing, the largest number you can represent is represented by the weight of the most significant bit. That dictates how many bits you have, that dictates. Whereas the smallest difference between two numbers, or whether the smallest number you can represent, is represented by the weight of the least significant bit. So anything larger which cannot be represented by the most significant bit is called an overflow, and anything smaller than the weight of the least significant bit is called an underflow. You cannot represent something less than the underflow, and you cannot represent something greater than the overflow. Okay, this is if you use finite number of digits. But as I have told that a representation which requires finite number of digits in one base, particularly a fractional number, may need infinite number of digits in another base. You can easily take an example and see. One more point to be noted is that if you add leading zeros to the integer part, if you add leading zeros to the integer part, so that means if you have am plus 1, am plus 2, all these digits to be 0, the numbers remain unchanged. So if adding leading zeros to the integer part doesn't change the value of the number. Similarly, adding trailing zeros to the fractional part to the right doesn't change the value of the number. Okay, so this fact will actually be useful while we build a number of circuits, while for manipulating the numbers. This thing will be important. Okay, all right. So with this basics of the number system representation only for positive numbers. We have not yet talked about negative numbers. Let us see the simplest operation we can do on two numbers, which is addition. Let's start with just with a very simple task of adding two single digit numbers. Okay, adding just two single digits. Let's see. Let's try to just forget about this result and carry. Let's see. Suppose I have two binary numbers 0 and 0. What is the sum? Sum is 0. So the binary representation of that is 0. Let me write it this way. Okay, so 0 plus 0 is 0 in binary. In fact, as well as in decimal. So 0 plus 1 is 1 in decimal and also 1 in binary. Okay. So what I will do is that let me let me do it like this. What is 1 plus 0? 1 plus 0 is 1 in decimal again and 1 in binary again. What is 1 plus 1? It is 2 in decimal. And what is it in binary? It's 1 0 in binary. Okay, so you need two binary digits. You cannot represent 1 plus 1 using single binary digits. So let's make it a convention. Let's represent all these four sums as two-digit binary. So 0 plus 0 in binary is 0 0. 0 plus 1 is 0 1. 1 plus 0 is 0 1. 1 plus 1 is 1 0. Okay, so these are the corresponding two digits number. What I do, since now I have two digits, I represent this by two names. So this thing, the first digit I call as carry, and the second digit I call as sum. Okay, sum or result. Sum or result. Okay, so this is very simple. So instead of storing the result, naturally you cannot just store the result in a single digit because 1 plus 1 cannot be stored using single digit. So I represent by two digits, and the first digit of the result I call as carry, and the second digit of the result, the significant digit of the result I call as carry, and the less significant digit of the result I call as sum or result. So this I have written down here. This I have written down here. Okay. Well, it looks like a truth table. I will see how to use this truth table later. Okay. So this is about adding single digit. Now let us try to add multiple digit, and let's see how this carry and sum can be used. So this again, all of you have done since your primary school. I'm just doing it for the binary. You have done decimal in your primary school. I'm doing it for the binary. So let's say I want to add two binary numbers. I'm not writing their decimal equivalent. I don't think I need to verify them. So I want to add two binary numbers 0 1 1 0, two 4-digit binary numbers, and 0 1 1 1. Okay, so now let's apply this previous rule of adding two single bit numbers. So I want to add these two single digit numbers 0 1. What I would get, the result would be 0 1. The most significant bit is 0, which I call as a carry, and the least significant is 1, which I call as sum. Okay, so sum is 1 and carry is 0. In other words, you can also, so this is the result of adding the first column of the least significant bit. Other words, this also, instead of this decimal kind of representation, you also can think of it as a rule. That is, if you add 0, 1, you get result 1 and a carry of 0. Now let's go to the second column. Just like you do addition in decimal, you now need to add the carry as well as these 2 digits of the inputs. So you can do it in 2 steps. Now the rule is that if you add 0 and 1, so 0, 1, 1, you get 2. Okay, and you 2, you know the sum would be 0 and the carry would be 1. Look at the previous slide. The sum would be, so if you have 0, 1, 1, which is this case, the sum would be 0 and the carry would be 1. This also again you can think of as a rule. So the sum is 0 and the carry is 1 and the sum is 0. And this you repeat. Now I have 1, 1, 1. If you have 1, 1, 1, you can think of it as 2 addition. So you have a sum of 1 and a carry of 0. This again also you can think of it like this. So if you have 1, 1, 1, which is 3 in decimal, is equivalent to 1, 1, which is carry equal to 1 and sum equal to 1. So you have sum equal to 1 and carry equal to 1. And now you have 1, 0, 0, which results in a sum of 1 and a carry of 0. So the final result is 1, 1, 0, 1 with a carry of 0. Okay, so this way you use the rule for single bit addition over multiple columns with a carry. All right. So now let's think of this as a now let's try to, well, our next goal is to, we'll first build a circuit to add 2 single bit numbers. Then we'll use that circuit to build a circuit to add 2 n-bit numbers. Okay. So now let's look at, what I have done is that I have copied this table, this addition table, as a truth table here, where these are the inputs. You know, 0, 0 is 0. It has a sum 0 and a carry 0. 0, 1 has a sum 1 and carry 0. 1, 0 has a sum 1 and carry 0. 1, 1 has a sum 0 and a carry of 1. The 2 bits of the result. Okay, so you have, so this looks like a truth table. So let me think of a box whose as a logic circuit, as a combinatorial circuit, whose inputs are this, as a logic circuit, whose inputs are this A and B. A and B are the input, and the output is the sum and carry. These 2 bits are the output, sum and carry. Okay, let's try to do this. And I'll call this box as a half adder. Why I call it as a half adder? Because it is adding, you see there are 3 things to be added here. You need to add the carry, you need to add the 2 inputs. So there are 3 things that you need to add. I'm not doing that. I am just considering this case where there are only 2 things I need to add. If I add only these 2 things, I call it half adder. When I have an carry kind of thing here, the first this thing, so this 1, 1, so this top thing, this carry thing, I'd call it as a full adder. If we ignore the carry, I call it as a half, carry as an input, carry as an output, I call it as a half adder. Okay, so let's look at the truth table. So as if this, what is the logic for if we express A as function of A and express S as a function of A and B, what is the logic? Can anybody tell what is the logic of S in terms of A and B? Just look at the truth table. What kind of logic it is?
XOR.
XOR. So this is the XOR gate. So S is this. There is another way of looking at this. If you look at the rows where S is 1, you see A is 0. So you take the complement of A and multiply that with b, since b is 1. This is the first row, or the entire thing with the second row where a is 1 and b is 0. So you take the complement of b. Okay, so this is the function for a. So this is the XOR gate. That's what I have done. I have denoted S as an XOR of A and B. Similarly, if you look at C, you see that it's a simple AND gate. So that's what I have done. I have ANDed A and B, and I get AB. All right. So this is the simple half adder circuit. In fact, if you don't want to use an XOR gate, you want to use the basic gates, like the basic gates are AND, OR, NAND, NOR, and NOT. These 5 are the basic gates. How do you do? You can still use this formula to do it for the basic gates. Let's see how to do it. So you have A, you have B. You can just look at this formula. So is A not A and B? So this is not A and B. This pen is not good, that's why. So this is the first term. This is A, not B. And similarly, you have a second term. You put a NOT gate, put an AND gate here. This is A, B bar. And then you put an OR gate. And you get S. And C you get simply by putting an AND gate. This is C. All right. So this you can think of, you can implement this using basic circuits also, basic gates also. Okay, just one thing I'd like to mention is that since we are all computer science people, we are always worried about time complexity. See, these circuits, these gates, they have a delay, they have a time delay between the time we put an input signal. So the time you put an input signal, so the time you get the output signal, there is a delta delay. There is some delay. As it turns out, because of the circuit implementation, all the basic gates, the AND, OR, NAND, NOR, NOT, they have the same delay delta. So each of these gates have a delay of delta. Okay. So what is the total delay of getting the carry from A and B? It's delta. And what is the delay in getting the sum from A and B? You can see it has to pass through 1 delta, 2 delta, 3 delta. So it is 3 delta. Okay. So what it turns out, you get the carry easily in less time, pretty fast, but you get the sum after in thrice time of that 3 delta. So the delay for getting the sum is more. But this is not enough for us. This half adder is not enough for us. We need to do this kind of addition. So basically, we need a circuit. So the least significant bit is fine. A half adder would do here. A half adder would do here. For the next column, we need to add 3 terms. We need to add 3 terms. Okay. So you need another kind of circuit, which, and after adding these 3 terms, the output is again 2. Output is a sum and a carry. Sum and a carry. Okay. So you need some kind of full adder circuit whose input would be A, B, and this carry, which we call as the carry in. Carry in. The third term, and the output would still be sum and carry out. Okay, so the rule that I mentioned in the previous slide about this this addition, this rule of 1 plus 1 plus 1 is 1, 1. This rule, I have written it down as a truth table. I have written it down as a truth table. What is the truth table? If A is 0, B is 0, carry in is 0, output sum is 0, carry out is also 0. If input is 0, 0, carry in is 1, sum is 1, carry out is 0. If input is 0, 1, carry is 1, carry in is 1, sum is 0, carry out is 1. Similarly here, look at this case, is input is 1, 1, carry in is also 1, carry out, sum is 1, and carry out is also 1. Okay, so this is the table for the ladder. And you can naturally see why I'm interested in this full adder, because I can I'll use this for adding n-bit numbers. Okay, now let us look at the logic. Let us look at the logic. So you see that again, well, one simple way of finding the logic for is that you look at the output, identify all the rows which have 1. Identify all the rows which have 1 and just look at their values of the input and see if they are 0 or 1. If they are 0, you put the complement, otherwise you put them as it is. Okay, so if you do that, so S would be A bar, B bar, C, A bar, B bar, C, and the next thing. Did I write this? This will be this. Sorry, this is this. So it is A bar, B, C bar, A bar, B, C bar. Okay, so this is the logic. Again, if you have access to a 3-input XOR gate, you can write it as the A XOR B XOR C. Similarly, if you look at the carry out, you can similarly write it. You can write the carry out as AB plus AC plus BC. Okay, see this again I am not working out. I think from your digital electronics you know this. I am not writing this again. So C carry out C0 CO would be AB plus AC plus BC. Okay, so I have copied the truth table again. Let's see how to build them using a circuit. How to build them using a circuit. All right, so if you don't have a 3-input XOR, you can implement that using 2-input XORs. This is, you know, they are associative. XOR is associative. So if you have A XOR C, you can as well write it as this. You can as well write it as C. So that's what I have done. I have written the sum as A XOR B, entire thing XOR C, entire thing XOR. So this is A XOR B, and this is C. So this is this. And let's look at this. This is what is this? Is this correct? Okay, all right. So this actually you can write it like this. So what is this? This is A XOR B dot C and C, and this is AB. So this is A XOR B C plus AB. Can anybody tell why this is correct? Why this is the correct full adder circuit? Because the original equation was let us look at the original equation. It is A bar B bar C plus A bar B C bar A B C A B bar C bar A B C. Can anybody tell why this is correct?
So AB is multiplied like AB and C plus C bar. So
right,
it can be expanded that way.
It can be expanded that. So see, this is an see I could have done this entire thing by a much larger circuit. I could have represented this by a much larger circuit. Okay, so this how many? This would be 3 gates. This I could have represented by 4 3-input AND gates and 3 2-input OR gates. Or if you have only 2-input AND gates, this would require 6 AND gates, 3 2-input OR gates. I would require much more number of gates, but by this simple transformation of the logical expression, using the output of this XOR already, you would get a smaller circuit using less number of gates. So this is an illustration that the reason this logical transformation of one expression to another is important is that by doing a number of intelligent such transformations and maybe reusing the intermediate outputs, you can have a much smaller circuit for doing the same job. Okay, and by the way, this entire thing, this full adder circuit, I could have also implemented using 2 half adder circuits. What would the half adder circuits do? It's intuitive from this definition of this. See, I have 2 input and the carry is I do a half adder of 2 inputs only. I don't have a full adder so that I can add 3. So how do you use that? Let's say I have a half adder which can add 2 things. So A, B are the input, and the output of the half adder I do is that the some part of the output of the half adder goes as input of another half adder. Okay, so basically what I do is that I add 1 1, I add 1 1, whatever is the output, that output and this carry together I feed to the second half adder. So the output of the first half adder as well as the carry in input goes to the second half adder. And the carry of the first half adder along with the carry of the second half adder, they are ANDed, and that goes out the carry out. This you can easily verify. This I am leaving as an exercise. This you can easily verify. And the output of the second half adder goes as the sum. So this, okay, I'm not doing it. You please do it. You just like this and verify, you get the same truth table. You just do it. Okay, so now let us come to the final goal, which we'll do in today's lab. You have a n-bit parallel adder. That means I want to add n bits simultaneously, not just 1 bit at a time. So what I do, there are many schemes for doing this. They have their advantages and disadvantages. The simplest scheme is something called a ripple carry adder, which just encodes this approach, the simplest addition primary school approach. So you at the initial stage you only need a half adder, there is no carry in, and the output of the first stage goes out. The carry of the second stage goes as input to the carry of the first stage ripples to the input of the second stage. Okay, so this is what I do. So let's see. So this is okay. Input also I have a first digit, the rightmost column also I have a full adder. So it's carry, which is maybe permanently set to 0. In fact, I could have replaced it by a half adder. The input to this full adder is A0, B0, which are the least significant digits, and the carry in, which the first digit is 0. The output is S0, and the carry out of the full adder is the carry in of the second stage full adder, the second digit full adder. So there is one full adder for every digit. The sum goes out as the sum. The carry out of the one stage full adder is the carry in of the next stage full adder, next significant bit full adder. This simple addition, how you do, you repel the carry to the left. You carry the carry to the left. Okay. So if you just cascade a set of such full adders so that the carry out of one is the carry in of the next stage. And if you build this entire circuit, the S0, S1, the sum output of each of the full adders would give the sum, and the final carry out would give the final carry, would give this, would give the final carry, this one. Okay, so if we call Ci, so if we call Si as the sum output of the ith stage, you can see the output sum Si is Ai, because each of these are full adders. Each of these are full adders. So Si, Ai, XOR Bi, XOR Ci. The carry out of the ith stage, since these are again individually full adders, is Ai Pi plus Ai Ci plus Bi Ci. Okay. Of course, correctness of this you can easily. It's not 2xn-1 gives the sum, gives the carry. C out, final C out gives the carry out. You can easily verify that. Okay. So, so this is a simple cascade of 1-bit full adders to a n-bit parallel adder. There is some bit complication here, because we have already seen before that this has a delay of delta and this has a delay of 3 delta. This has a delay of 3 delta. If you apply A0, B0, A0, B0 at time 0, you will get S0 at delta, S1 as 2 delta. Oh, no, S1 not at 2 delta. I have to wait. C0, or let me call it C1 at 3 delta. And since I'm waiting, so from C1 again it takes another 3 delta, so it would take 6 delta, because after I get C1 I can compute S1 and C01. So S1 would come after 3 delta from the time C1 comes, so it will come at 6 delta. And no, it will come at 4 delta. Just 1 delta. S1 comes at 4, whereas C2 comes at 6 delta. C2 comes at 6 delta. Okay, from the time 3 delta from the time C1 arrives. So if we call this as the time at which C1 arrives, this comes at delta from that, this comes at 3 delta from that. From the time this arrives, this comes at delta from that, this comes at 3 delta from that. So if you keep on adding them, you will see that the final carry comes at, if you have an n-bit adder, it comes at 3n plus 1 delta, which we write it as O delta, order delta, because this is, sorry, order n. If you have an n-bit adder, it comes at order n delta. Okay, and the S1, they also, this is not 3n plus 1 delta. This the final result, this Sn minus 1 will come at 3n minus 1 delta. You can check that. So this final Sn minus 1 also comes at order n delta. Okay. So even though this is a simple circuit, if n is large, the delay will also be large. You need to wait for some time to get the delay. The delay will also be large. So even though in terms of the number of circuit elements, this is less. This is a very small representation. You need less number of gates, but the delay is high. It's order n delta delay. Order n delay for n-bit addition n-bit. We'll look at more intelligent circuits which uses more complex logic, as a result more gates, but it will require less delay. It will have less delay. We'll see that in the next class. Okay, thank you. So I think I'll end here
Sir,
what I, yeah. Please tell.
actually I got registered recently